Hi everyone, I'm Hannah Nyren. I'm the head of digital marketing and analytics at the MIT Press, and I'll be your host. Today we are speaking with two very cool authors, Claire Asher and Chris Foreman, authors of Brave Green World. And we're really excited to have them here today, and they have a great presentation for us with lots of beautiful visuals. And they're going to read some excerpts from the book. So how are you doing? How's it going, Claire and Chris?
I'm very well, thank you. Enjoying a little bit of sunshine here in the UK.
Yeah, and weather's pretty great over here in Chicago as well. So yeah, doing great. Yes, thanks for having us. Yeah.
Great. Glad the sun is shining somewhere. Here it's a bit gray, but not too bad. Not snowing. It's always good when it's not snowing.
Definitely.
All right, to start off, could you tell us a little bit about yourselves, starting with Claire?
Sure. So I'm a freelance science writer and communicator. I have a PhD in the genetics and evolution of ants. And nowadays I mostly write about kind of conservation and sustainability issues, but also a little bit of animal behavior, evolution, and genetics.
Cool.
That's
yeah.
awesome.
And I'm Chris Foreman. I'm a research scientist at Northwestern University. Originally, I was a physicist, and I've kind of moved into materials science. And I'm driven by sustainability and how we can sort of really transform the materials world and build a circular economy. That's my jam. So yeah. And I gave a talk at the Cheltenham Science Festival, which is how I met Claire, actually, which was pretty cool. What about natural nanotechnology? And the book kind of grew out of that, really, because we published an article together, right?
Yeah. I saw Chris's talk and I thought it was just really fascinating and a really kind of novel way of looking at the world. So I approached him and ended up writing an article for How We Get to Next. And then just felt like there was more there. So we chatted a bit and started drafting the book together.
Yeah, it just grew into a book. So this is what we've got today.
That's amazing. So before we begin, can you just describe this book in one sentence?
Yeah, it's a brief survey of the technology that we think will underpin a circular economy.
Perfect. All right, so let's begin your presentation.
Okay, cool.
Okay. So today we just wanted to give you all a little bit of a taster about what Brave Green World is all about. And I thought that I would start by reading an excerpt from the introduction. The rings of a tree tell a story about the life of the tree and the environment in which it grew. But what is humanity's story? Will it be a blackened layer of fossilized smartphones in the footnotes of geology? Or will it be a story like Daintree Forest in Australia, one of the oldest surviving forest ecosystems in the world, whose current inhabitants boast a direct lineage thought to be over 100 million years old? To envisage a 100 million year long story for humanity, we must imagine a world where every generation returns the materials they use to the soil, air, and oceans in a way that enables future generations to use that material too. A world without waste or pollution. The transition to such a system, called a circular economy, depends greatly on science. In this book, we explore the science that could take us there. Our current way of living is destined to change fundamentally in the next few decades. Exactly how that happens is a decision that will be made collectively by all of us. The materials we use to create our new world will depend on the technology at our disposal, which will be determined by the science we perform today and the politicians we allow to govern us. Balancing the long-term prospects of other people's great-grandchildren against our own short-term interests is not a trade-off that many people give much thought to. But natural systems suggest there is a way to provide technological luxury to us all, at the same time as guaranteeing a positive future for everyone's children. Imagine if our future electronic devices could grow from the buildings around us like a tree bears fruit, and throwing away an old device was more like composting a discarded apple core. Smart materials and innovative molecular manufacturing inspired by natural organisms could trailblaze the way to a fairer, more sustainable society that boasts a hyper-efficient, innovation-driven circular economy. An economy equipped to address the multifaceted challenges of climate change, biodiversity loss, and inequality, while bringing countless benefits for all of humanity. In the following pages, we set out our vision of a future where 10 billion people can flourish on Earth indefinitely, without exhausting our planet's raw materials or harming the other 8 million species on the planet. Such a circular economy could even drive our expansion to other planets, and that is a tale we want to hear.
Yeah, definitely. And now we're all familiar with the concept of circularity. You know, what is this talk of a circular economy? I mean, in essence, it's the water cycle. Water evaporates from the oceans and falls as precipitation. So we're all really familiar with this idea that material on a planet moves around in these great circles, great big circles. And it's a never-ending cycle that's driven by energy from the sun. And every single material on Earth, every element has a natural cycle like that, whether it's nitrogen, phosphorus, carbon, and so on. And a circular economy is one that recognizes that planetary material supply is finite and cyclic in nature. And it's one in which every single item, every single material that we use gets recycled. And typically it's kind of split into sort of two main flows. We've got these kind of biological flows, natural sort of materials, proteins and you know, nitrates and phosphates and so on, moving around in this loop. And then you've got a more sort of technical materials, metals and ceramics and so on, going around here. And it's such an economy. Once materials have been gathered, you know, they just move in these never-ending loops. And to make it work, companies have to think about their waste material as if it was a product that they're supplying to someone else. And so it's really about transforming mindset, and it also completely changes our relationship with capital. So just as forests and natural ecosystems regenerate soil continuously, a circular economy regenerates capital locally. So it completely changes the way that we interact with infrastructure and material flows. Once you've brought material to you, it's yours, you can recycle it. And there's 5 sort of key principles of a circular economy. There's no beginning or end. Smaller loops are more profitable. There's no point in importing carbon from China in the form of t-shirts when you've already got like a load of carbon right here. Slower loops are better managed. So, you know, moving away from these fast moving consumer goods where profit is based on the volume of material flowing, rather use slower loops to get better value out of the materials that you've got. And there's also this continued sense of ownership. You know, you own these products. Once you have them, they're yours. You don't throw the materials away unnecessarily. And there's still a concept of a free market built into the circular economy, but it would tend to be less about sharing materials. You know, if everyone's got raw materials everywhere, you don't need to trade materials. It's more about trading designs and patterns and ways of implementing those patterns. And just to contrast that concept of a circular economy, I want to read a section about our linear economy. You know, what's wrong with the current system? And so here's an excerpt from chapter 3. Like the early life forms we discussed in the previous chapter, throughout human history, we have opened up new opportunities by changing the fuel that we use. When Stone Age humans discovered how to burn wood to create fire, this simple innovation led to a step change in our cultural evolution, keeping us warm, improving our diets, empowering humanity's activities for 1 million years. Similarly, the development of the first steam engines, which burned fossil fuels like coal to generate mechanical movement in a turbine in the late 17th century, was key to the Industrial Revolution. Both wood and fossil fuels are a source of solar energy, trapped on its brief detour through Earth's atmosphere and stored in living cells. And these indirect sources of solar energy are high intensity, meaning they release large sudden bursts of energy when we burn them, more like the explosion of a stick of dynamite than a living creature metabolizing calories. And since we discovered these high intensity fuels before we learned to harness solar power, our industries have adapted to make use of large bursts of energy to manipulate matter into useful forms. A wood-burning fire and an electrical power station both produce outputs that have the right chemistry to fit into natural global cycles of elements. In addition to electrical energy, power stations release mainly CO2, water, and heat, which are exactly the same outputs as cellular respiration. The problem is the ubiquity of these processes produces CO2 more rapidly than the natural world can absorb through photosynthesis, exceeding the planetary boundaries. Why is the CO2 output so high? Because our industries have standardized around materials with high energy barriers, such as steel, aluminium, copper, and glass, which must be softened by heating to make them malleable enough to work with. Performing these high energy processes in large centralized power plants and factories allows us to exploit economies of scale, but it also results in lengthy and often complex transport networks for our energy and materials. These distributed supply chains are the cause of a great deal of waste. Operating over much shorter distances, biological cells raise in size from about 1 to 100 microns, would create fresh scope for material efficiency through the integration of systems. Just as photosynthesis and respiration are implemented within an individual plant cell as part of a much larger ecological pattern, matter could move between human energy and industrial processes at a molecular level to create a global circular economy. And that focuses our attention away from energy onto ways of organizing matter. So that's kind of a brief introduction there, to the problem. Now, this is a really cute analogy that I dreamt up quite a while ago, and we enjoyed it. We put it in the book because it's just quite succinct. There's this idea that we can think about Earth as a giant Rubik's Cube. And you can think about each square on here as typically like red, green, yellow, different colors. You can imagine that red was iron and yellow was sulfur, or whatever. And you can shuffle it around and so on. And you've got to put energy in to reorganize that material. But you're not destroying any of the material that's there, just moving it around. And the question, of course, is what pattern do we want to implement? And why would we assign a higher value to one arrangement than another? And of course, that's what economic studies is like, the value of different arrangements. But we're not here today to argue over which pattern is better. What we're here to do today is to think about tools for moving the materials locally. And of course, we know that when we move things on Rubik's Cube, we mess up the bit we've already made. And that's sort of an analogy for the global effects that we have in our local operations. So we're getting this idea of global and local at the same time, in the same processes. And ideally, we want to be able to take every single atom on the planet and assign it a valuable role, just as every atom in a biological ecosystem is doing something useful. So we can learn a huge amount from biology about how to build a system like this, how to improve material efficiency and drive it with sunlight. But to do that, we are going to need a set of tools.
So in the book, we identified a set of tools that could help us to achieve this kind of molecular scale reorganization of matter within a circular economy. Most of these tools are already available and are the result of decades of scientific research. The final piece of the puzzle, we think, might be chemical computation, which is one of Chris's current areas of research and is absolutely fascinating. And we're not going to go into that in detail today, but there is a whole chapter on that and how we can make matter perform computations, which is the basic principle of chemical computation. This is still an idea that's very much in the research stages, but we think it could become an important part of our circular economy in the future. Today, I'm going to talk briefly about the three other tools that we discuss in the book: 3D printing, artificial intelligence, and synthetic biology. So 3D printing is a 3D printer is infrastructure that combines streams of matter, energy, and information to create a specific workpiece, and it produces very, very little waste. As this technology advances, we're getting better and better in organizing materials in this way. And as this beautiful image illustrates, the geometric freedom opened up by 3D printing is already inspiring novel designs that we just could never have come up with before because there was no way to realize them. And all of this can be achieved without changing the infrastructure, without changing that 3D printer. Just change the information you supply to the printer and a completely new pattern emerges. And 3D printers can now handle an amazingly diverse set of materials. So it's not just the traditional plastics. We can print with metal, concrete, ice, even jelly. And one of the reasons that we're interested in 3D printing is because this type of additive manufacturing is really similar to how biological organisms produce the proteins and other products they need to function. So inside every single cell of your body, there are meters of DNA, all tightly coiled up, and they contain all the genes that encode every single protein your body might ever need to make, along with, a bunch of regulatory stuff. And this DNA is the information input for an additive manufacturing process, equivalent to the data sent to by the computer to the 3D printer. So proteins, which are, kind of the fuel of everything that goes on in the cell, proteins are made up of amino acids, and they come in 20 different types. So all these amino acids are floating around in the cell, and if they match the instructions encoded in your DNA, then they will be added to the growing protein chain by an amazing little molecule called the ribosome. So the amino acids are the material input, equivalent to the PLA or whatever material you're putting into your 3D printer. The ribosome acts as a printhead, reading information encoded in your DNA and turning that into a finished protein. So this gives biological organisms complete digital control over the manufacturing process, and that principle has underpinned the evolution of all life on Earth. And the fact that this system is shared by all living organisms gives us the potential ability to reprogram this biomolecular 3D printer so that we can produce the proteins that we want. And this field of research is called synthetic biology, and we discuss it in depth in chapter 5 of the book. Now, a key aspect of all of this is that biology is using materials that have a really low barrier to reconfiguration. So you don't have to apply very much energy to change the shape of the protein or to add or break off amino acids. And this means that cells can do all of this with solar energy harnessed through photosynthesis. So if we were to change the materials we work with on a daily basis, then we could make it much easier to use renewable energy sources to power our manufacturing processes, just like living cells do. And so then the final piece of the puzzle is artificial intelligence. You know, we come at artificial intelligence from two different perspectives. So artificial intelligence has developed really rapidly over the last few decades. We all interact with various forms of AI every day, from the smart assistant in your phone to the algorithms that serve you ads on Facebook. And AI is a data-driven approach. So machine learning works by providing the computer with huge amounts of data and allowing it to find patterns, identify patterns that humans might struggle to find. So as I said, we see two kind of different angles in which AI could be useful to help us transition to a circular economy. Firstly, it will definitely be used in smart factories of the future to help monitor manufacturing, redivert resources, look for wear and tear. But taking that a step back, perhaps we could also use machine learning to actually find the materials that will form the basis of these advanced manufacturing processes in the first place.
In fact, that's one of the areas of research that I'm working on as well, is how to use AIs to research material properties. And I wanted to read a little section from the book about this. The ability of artificial intelligence to find patterns in huge data sets, evaluate complex simulations, and make predictions about novel data or future conditions will make this technology an invaluable asset in our search for the right building blocks, materials, and emergent properties to form a circular economy. But before we can start to explore the vast space of materials in front of us, we need a standard method of representing them and a way to search this library of standardized representations. Energy landscapes offer a useful framework to help scientists and engineers hunt for materials and are based on the internal energy barriers that we have mentioned. The energy landscape for a particular molecule is a mathematical function constructed by computing the internal energy barriers between every possible arrangement of that molecule. And the final function resembles a mountain range. Some arrangements of the molecule have higher energy, which corresponds to mountain peaks, and other arrangements have a lower energy, which corresponds to the valleys. And if we compute the energy landscape, we can know everything about a molecule's behavior. The size of the peaks between the valleys determines how hard it is to rearrange the molecule as it moves around the landscape. For example, a metal might have several deep valleys corresponding to different crystalline structures. To rearrange this metal, we would need to heat it up considerably, applying a lot of energy in the process to overcome the high barrier walls. For a molecule like a protein, on the other hand, the surface might be more like a range of hills with one deep valley. And this deep valley corresponds to its folded state with many small barriers on the way. Thus, the molecule is able to explore different conformations with less input energy, the defining characteristic of soft matter. We could imagine every material that could exist or has existed, every atomic configuration of every element and compound, and represent it as a gargantuan digital library of energy landscapes. Each floor and corridor of the virtual library would house landscapes relating to similar molecules. Proteins here, DNA there, metals there. Each book in the seemingly endless library would contain the landscape for that material, itself a seemingly endless vista of undulating hills and valleys. Seemingly endless, because from the point of view of someone stood within that material design landscape, the possibilities seem infinite. But the point is that they are not endless. There is a finite number of possible materials that could ever exist, given the available elements and basic physical laws. Finite, but extremely large, is what computers excel at. Now, so far we've talked a lot about the local behavior of materials, like the energy barriers and how that can relate the planetary energetic processes to the local material ones. But we need a way of building in that global connection from our local environment. And the internet is a really obvious choice for doing that. And this is exactly where all these AIs are going to hang out, building this huge library of materials that we could locally sort of interrogate and download for a particular application that we need in our local systems. And the internet is a tool which we talk about, the history of how it's evolved to give us a clue about how we could maybe evolve our own sort of technology platforms. And it has both local and global aspects to its nature. So there are a set of rules that everyone on the internet has to obey. And if you obey those rules, they're called TCP/IP, the internet protocols, which were figured out over the course of several decades by trying to plug military network ARPANET into the National Physical Laboratory network in the UK, trying to figure out how to get these networks to talk to each other. And the resulting model that emerged is this layered model. It's called a stack of technology. And at the bottom of that stack is a physical layer, the actual means by which information is moved around, whether that's Wi-Fi or Ethernet or some other method like carrier pigeon or whatever it is, doesn't matter. And each layer abstracts out functions such as dividing data from your email into packets, assigning addresses to those packets, and then sending them off across the network to their destination. And if those rules weren't global, then you wouldn't be able to join in with the conversation. But the fact that you have a global set of rules in no way restricts the immediate local input that you could have into the system. Whatever the web page is, it can have any information on it you like at all. And it can be transmitted globally, which is fantastic. So it turns out that the internet is not the only globally local system that's already been implemented. In fact, the trophic layer in biology is a pretty good example.
Yeah, so like the internet technology stack, ecosystems are arranged into trophic layers with different organisms performing different roles in the ecosystem. So at the bottom of this technology or biological technology stack, you have the primary producers, and they harness solar energy to grow. Above the producers are consumers, and they feed on plants or other animals to get their energy. And each layer, some energy is lost as heat, so that by the time we get up to the top predators, the ecosystem can only support a relatively small number of them. And the whole system is connected, the loop is closed by the decomposers who break down dead material and return it to the soil again for other organisms to use. So although ecosystems can be incredibly diverse, every organism is using the central dogma we mentioned earlier, where the ribosome printer uses information in DNA to produce proteins. And this architecture is present, as I said, in all living organisms on Earth. And each cell in every single living organism contains not only the information about what proteins to make, but also the instructions for how to manufacture them. And this nesting of kind of biological additive manufacturing within an ecosystem embodies the circular economy idea of globally local. So if we took inspiration from this biological stack, perhaps we could build a platform technology that enables every single human to exchange matter and information, and manage matter in their local vicinity. And just like the internet, we can imagine a similar stack of technology making use of synthetic biology. And this is something that's already emerging. So for example, SynBioBeta is a global organization promoting advancements and collaboration in synthetic biology. And through this and other organizations, a kind of an ecosystem of different companies is starting to emerge. So at the bottom layer of this stack, you might have biological reagents, DNA strands, enzymes, model organisms. And then the next layer executes the manufacturing process. So we're thinking about robots performing precise chemical reactions in cloud labs. The third layer of the stack is the design layer. So that's some kind of like biological computer-aided design. And the final layer is the application, the final product, whether that be chemicals, food, drugs, or even whole habitats. And like the internet, each layer of the stack, you can work in each layer of the stack without a full understanding of the layers beneath, which allows people and companies to specialize in one area, just like organisms in a real ecosystem. So I wanted to read one more extract from the book, which brings together a lot of these ideas. And this is from chapter 3 of the book. It's called Another Way. Taking inspiration from the way natural ecosystems cycle resources and power their activities from low-intensity renewable energy, we can start to imagine an alternative to our destructive linear systems. Consider the exquisite balance of materials found in soil, water, and air. These gargantuan reservoirs The remains of countless generations and species are not homogeneous, but they provide an auto-regenerative bank of useful raw materials that we can exploit. Most importantly, these reservoirs are within molecular reach of all living organisms, thus eliminating the need for elaborate transportation systems. In a similar vein, the contents of landfill are not homogeneous. They represent a supply of the chemicals and materials that people need. And just as plants are able to extract nutrients from the mixed media of air, soil, and water, perhaps we could extract the materials we require from landfill. This prospect remains out of reach because our current manufacturing processes are not set up to use landfill as a resource. But if we could instead generate products that, at the end of their useful life, regenerated a reservoir of reusable materials like soil, the concept of waste would become obsolete. Although technological changes are needed for such a vision to become reality, the fundamental shift required is one of mindset, to view everything we produce as a useful material for another application, not as waste or a byproduct. Perhaps the biggest problem with the way that we make things now is that we have this concept of the end object. Such thinking inevitably results in linear processes to create this desired object, and what happens after its life has ended is often relegated to an afterthought. We will have to be much smarter than that with our materials if we are to transition to a circular economy.
Yeah, and indeed, this is a lot easier said than done. So in the book, we try to put all these ideas together to do a kind of thought experiment, to think about what kind of stack of technology you would need, how it would work, how could you pull together all these different technologies to create this kind of local global circular system. And what we end up with is this stack where you have some kind of raw materials input, landfill or something, and each layer is probably a different function. Like, so synthetic biology here, perhaps this might be, when you brew beer, what you're doing is you're using yeast to convert sugar into alcohol. So what if you created a more generalized version of that, where you could sort of say, I want to turn A into B, and I want to engineer a microbe which will live in my basement where plenty of people brew beer, and that would be like a sort of basement reactor, which would be basically capable of performing the necessary chemistry, grabbing energy from sunlight and doing a lot of basic materials reprocessing locally. And could you use that to generate some kind of feedstock, which you would then pipe to your local 3D printer? Plenty of 3D printers use liquid resins as a source of their material. And this would be like a sort of really complex mixture of nutrients, which you would then be able to add together using some sort of 3D printer. And the whole thing, of course, being controlled by some sort of IT interface, so that the local user can just say, I want to have X, Y, Z, and put it into their house system, and then it might manufacture that slowly over, a day or 2 or 3 days. And then using local raw materials as this source. And of course, when you finished with it, you could do something that was a reverse process, grind it down, have biology consume it, and turn it back into raw materials. So this is the idea of what we call an SBAM stack, synthetic biology additive manufacturing stack. And of course, we could take that and create the peer-to-peer network where, locally we're sharing materials. We call this idea the Synthenet. It's like synthesizing materials. But the top layer is basically your regular internet. And then you've got these layers implemented everywhere, in every building in your vicinity, which is then, we want to make something very clear. This is a thought experiment. This is an idea of what it might look like. And we put this out here as a provocation. We want people to say, this is just fanciful, and say exactly why it's fanciful. Why can't you do this? And what is it, the problem that you couldn't just do this straight away? And then that will help us figure out what the exact challenges were to learning how to build a protocol like this. And of course, we came up with this idea of city blood. This city blood would be like a really refined sort of multi-phase flow, which is, if it's feasible to take sewage, which is a multi-phase flow, away from every building, then presumably it's possible to bring a multi-phase flow in and use that as a kind of feedstock or a way of sharing waste, and then having an internet layer on top communicating. The hospital might want some titanium to build a scalpel or whatever, and of course this would then create a really well-controlled interface with our natural systems, like wild ecosystems and so on. So we can conceive of building this kind of technology stack that links things together. And our version of the Synthenet is somewhat science fiction, but it turns out there's not so science fiction elements to it.
As Chris said, the Synthenet is a thought experiment. It's a way for us to explore the ideas we've brought up in the book and to imagine just how far we could take a system inspired by biological organisms. But it's also really just an advanced version of industrial ecology, and that's something that's already around today. So industrial ecology is when multiple industries work together to exchange waste materials so that they can be usefully reused rather than going to landfill or to the atmosphere. And we talk about two great examples in the book. We talk about Wissington Sugar Factory in the UK and Kalundborg Eco-Industrial Park in Denmark. And on the slide here, you can see a nice kind of stylized diagram showing what happens at Kalundborg. So Kalundborg was established in 1972. It's the world's first industrial symbiosis. And frankly, the fact that it's still operational and profitable today proves that this concept really does work. It includes 11 companies and 30 different material exchanges. And despite the fact that it's all centered around a coal power plant, it has virtually no greenhouse gas emissions because everything is recycled into another industry before it has a chance to be admitted into the environment. Next slide, please. As we said, the Synthenet is a thought experiment. It's one possible future that we could aim for. But if we want to create a circular economy, whatever that circular economy might look like, we need to start putting the building blocks in place now. and we believe that everyone has a really important role to play in shaping our future circular economy. So just briefly, at the policy level, we need to make sure that the scientific research we're funding now is compatible with the circular economy and help to focus more on more interdisciplinary research that brings different groups of academics together. Governments can also enact policies that help to create the right environment, the right incentives for emerging industrial symbioses like Kalundborg to flourish. As consumers, we can influence the direction the economy takes, not just in the brands and the products we choose to buy, but in our decisions about where to bank, where to invest, which politicians to elect. And business owners have a really important part to play, from small family-run businesses all the way up to multinational corporations. And it can start with simple steps like working to improve workplace sustainability. And then in the longer term, looking for other industries for whom your trash is their treasure. And both of these things can improve sustainability and increase profits. So it's these kinds of environmental win-wins that we need to seek out. Finally, we see that we think that community-driven initiatives will be really important in this kind of, globally local system. So things like, community groups supporting a culture of repair, swapping, recycling, and creating communities around that. And lastly, how we manage the dialogue between these and other stakeholders. And ultimately, that's all of us, because we are all stakeholders in planet Earth. That will be crucial to making progress towards a circular economy.
Yeah, indeed. I'm actually a really big fan of a new form of democracy called deliberative democracy, which actually, you don't need permission from governments and big corporations to start building up local community discussions centered around these topics. So I think deliberation and deliberative democracy, which we talk a little bit about in the book at the end, is really going to be a crucial way to build mini publics that can address these kinds of issues. And we can start doing that on our own without any kind of permission from anyone. So that just about wraps up everything that we wanted to present just now. We're just going to say a quick few thank yous to all the people who helped make the book. It wasn't just us two, it was a real team effort. Particularly want to highlight Robert Brant's graphics. He didn't actually draw this particular image, I just realized that, but he drew some fantastic images throughout the book. And of course, Molly, who's here listening to us now, who's helped publicize us, and all the people from Unipress who have been instrumental in bringing this book to market. And we're really, really happy with the result. And we really hope that people enjoy reading it and that it inspires some fantastic conversations like the one we're about to have. That's the general idea. Thank you.
Thank you both. You did an excellent job.
Thank you.
While I'm waiting for people to ask their questions, don't be shy. Everybody can ask a question. We have time. Can you tell me a little bit more about the process of creating this book? Like, where did you begin? I know you met at a conference. You started with an article. How did it turn into a full-scale book like this?
I should just tell the whole story, shall I? So way back when I was doing my PhD, which was in protein engineering at Cambridge in the UK, I thought I came up with this idea of how could we grow like an iPod on a tree? How would you do it? What would you have to do? You know, and I took this. I wrote a talk. It was kind of a bit tongue in cheek, but I took an iPod to pieces and I found a biological analog of every single component in that iPod. And the talk was quite popular. People liked it, and I ended up giving it year after year when I went to postdocs and stuff, giving it to cohort after cohort of engineering students. And it's a really fantastic way of introducing people to biology. Engineers who haven't got time to delve into full biology, but to get an appreciation and to relate to it. And it works in reverse as well. And in fact, it was a version of that talk which I gave at the Cheltenham Science Festival, and that's where Claire and I, we started to write this article. We realized there's so much stuff to unpack. But then we decided to write a book, and that was totally Claire's idea, right? I would never have done it unless Claire had gone to me and said, let's write this book. And so we sat down. I remember it was a pub one afternoon in London somewhere, and that was fun. What was the name of the pub? Can you remember?
I can't remember.
Oh, it's in,
That's a sign of a good pub trip if you can't remember.
There we go. Yeah, and
we would have had a promotion for the pub too. But
yeah, that's right. And we just thrashed out the basic plan and overall plan of the book. And we spent about jumping at any point, Claire, but we spent about two or 3 years kind of thrashing out a proposal, right? Which we then sent to various companies. During which time I moved to the US and we became sort of remote projects. And then persistence was the answer there. Persistence and listening to feedback. And eventually Unipress picked it up and they had their sort of vision for what the book would be like. That was Kate Shanahan's vision, I think, this idea, this very colorful book. So that when you pick it up, it's like in sections. There's a lot of content in this book. It goes from basic fundamental physics of Earth right the way through to these advanced concepts like chemical computation. And on the way, it explains ecosystems and biology and how all this fits together. Huge amount of background pyramid knowledge going into that book. And so Kate wanted this idea that if you opened it on any page, that you could just see like graphics, paragraph explaining it, and you could sort of jump around if you wanted to, or read it straight. And then it took that was the point of starting to write the book, right?
Yeah.
And then
one kind of nice idea, the original talk you talked about can iPods grow on trees? I mean, it goes to show how long we've been working on this, that it's iPods, which is now pretty out of date, and what that's morphed into now is one section in each chapter where we try and talk about how we could make a biological smartphone. And we in each chapter we kind of approach a different angle of that. How would you make the screen? How would you make the casing? How would you help it connect to the world? And we had so much fun kind of figuring all of that out and looking to biology to see where we could find analogs of all the technology that we use today.
Yeah, and there it is, available for you, bookstores.
all the bookstores. It's kind of a whimsical approach to biology, looking at it through a technology lens. Did you guys come up with that on your own, or are there a lot of different people talking about it this way?
Many people are talking about this, particularly in material science research, like single molecule electronics, for example. When you think about shrinking a transistor, using a conventional lithography, they try to make smaller and smaller transistors, but they can't make them smaller that way. So to get more powerful computers, it means, well, eventually we're going to build a molecule-sized transistor. And so those people are like studying single molecule transistors. But then it turns out, of course, that biology is really, really good at single molecule electronics. Like all of these proteins are essentially like photosynthesis, an example. The respiratory complexes, they're huge proteins. And what we left out in this talk is that they fold around cofactors, which are little molecules like chlorophyll that have metal atoms in the center. So instead of having millions of metal atoms, you can have one metal atom in a very, very carefully curated environment. And you can move electrons between those metals. And biology is amazing at doing that. That's how photosynthesis works. That's how cellular respiration works. And we lay all this out in the book really clearly. And in fact, every living organism is part of a giant electronic circuit, where the ground plane of that is water. That's the low energy point. And then photosynthesis splits the water up, the electron moves around through sugar, gets burned in respiration in another organism, and then breathed out as water to form the water where it started. So that's a natural circular process. And the two halves, respiration and photosynthesis, link them together. So it's not entirely whimsical. It seems that way maybe, but when you dig down, it's exactly the same. It's exactly the same. And it's how do we, and there's a whole system for programming it conveniently laid on, you know, just put some DNA in and create another type of system. And that's what my PhD was about, was thinking about how to design protein systems to move electrons around. So it was natural for me to think about how we would build an entire smartphone this way. And, you know, it's hard. It's extremely non-trivial. It requires 9 orders of magnitude of iterative design processes. And I'm not under any illusions as to how difficult it is, but we've got to create the vision before anything like that can even begin to exist.
Yeah, I think it's really interesting to look at how we can find parallels for what we, you know, the technological developments we've made in biology. And, you know, you see this all over the place with bat sonar. And there's examples, I think, of like researchers actually trying to use squid and octopus skin, you know, how it changes color, using that to kind of as a way to create new technology. So there's this really interesting interface, but I think often as humans we think we did everything first, and you know, we didn't. Whatever you can think of, somewhere in the biological kingdom it will already exist.
I absolutely agree with Claire on that point, although there is one major caveat, which is radio waves. Okay, and
we had trouble with radio waves.
Yeah, like there's no real natural analog for a radio system. Like, there are long-range communications, like with sub-sounds, like, you know, elephants and whales can and lions also. But you know, no one uses electromagnetic encodes the way that we do electromagnetic information. That doesn't mean to say that you could. No, well, I mean, one thing that, you know, if you can accelerate charge, you can generate a radio wave. Probably because biology doesn't use lumps of metal, you don't do that. But anyway, I won't get.
But also, I think, you know, maybe the evolutionary pressures for living organisms to evolve radio weren't there because they, you know, the individuals that are so far away from you, you're not interacting with them, you know. So I think maybe it could have evolved if there was a strong pressure for that
that would be a fun experiment to try and put some proteins in a vat, get a machine learning thing to try and evolve a radio system. Yeah, and there are people who have actually looked at that a little bit, and some people claim that when they put filling in their tooth, they can actually pick up radio waves and they can hear it in their head, and that is really, apparently this is, it must be really annoying if that,
it must be,
and this problem is that no one else can hear it, so you've just got to take that person's word for it. But I think that I think that it may be possible to do something with it. That'd be fun.
Wow, that would be cool.
Yeah, I mean, you can certainly produce metamaterials or materials interacting with radios, so these are materials that have a sort of nanoscale structure, and they can kind of be like opaque to material or to particular frequencies. Sorry, I mean opaque to radio waves, or, you know, particular frequencies of radio waves. So you can put them, say, on the wall of a cinema and screen out mobile phones, or at the flick of a switch, make a room like a Faraday cage, and then turn it back on again. And now I can communicate with the outside world, that kind of thing. So you can certainly play games with materials that interact with radio waves and light systems as well, for sure. That stuff is happening.
I feel like you guys should have a kids show where you demonstrate all of these things.
Oh, yeah, that would be fun.
That would be great fun.
I sometimes do that. I got some friends who are teachers, and I just parachute into their classrooms and I just kind of like give a little science lesson in the classroom. And it's just a way to change up for the kids, especially throughout COVID. And it just keeps them a bit more interested. It's a lot of fun.
And you know, if you can't explain your research to a child, then you don't understand it yourself.
Right.
That's a really good one. We should tell that to everyone. That's the rule for writing a book. So we have a few questions in here. It seems like there are new recommendations for what the average person can do to be more eco-friendly every day. Do you have any advice you can share based on the book and or your scientific expertise? So how can we make the world more eco-friendly?
In our own environments, I mean, well, obviously things like recycling, definitely learning. one of the real challenges for sustainability is the fact that the manufacturing systems are so opaque. You know, it's really complex, massively complex transport, supply chains that make it really difficult to know exactly, even your coffee, whatever, where does that come from? Who knows, just flour and, So I feel like putting consumer pressure onto companies to sort of be clear about their transparency of where they're getting their materials from. Also, you can join local cooperatives for just, sharing equipment, tools. Like, why does everyone have to have a car? When I look around and I just see huge amounts of metal just sitting by the side of the road doing nothing. And I just think about the pyramid of carbon energy that the carbon footprint that was released making those cars. So just getting over this feeling that you've got to have a car, well, that would be one thing. And just sharing. Everybody uses Uber, and then you don't have to worry about parking. So it's these kinds of things, these kind of consumer habits that are going to make differences. But I think the single biggest thing we could do is eat far less meat, because there's an area the size of Africa or something which feeds the US with meat. And I think about that as well. I think about every single bar, restaurant in the US that you go to is selling burgers. I just think, how many burgers are waiting, just sitting there to be sold? And you add that up, and everyone has a burger every day. And you're just like, well, not every day. That's an exaggeration, but you know what I mean. I'm like, yeah. So you go, Claire. I'm going on.
I was just going to say, you just reminded me. So I've just been writing an article recently about sustainability in agriculture. And there was this amazing fact that they had that in Europe, I think it was 1955, the percentage of meat that people ate was 35%. That was the percentage of animal protein in the diet, was about 35. And since then it's gone up to 55%. Wow. And all the evidence suggests that actually that's not the healthiest diet either. So yeah, I completely agree. Like, there's not necessarily that. I think that there is definitely a place for livestock in the future. They provide a lot of really valuable services like grazing and manure, but we definitely need to be reducing that contribution of animal protein in our diets for sure, and really putting pressure on governments and on companies to increase supply chain transparency, because we have no power to change anything if we don't know what we're buying.
Yeah, and in fact, some technologies that might be helpful for reducing the carbon footprint of meat is, I call it lab kebab, where you go homegrown meat in the lab. So if you can think about that idea of going straight from a cell to a meat product, and when you grow it in a culture, and in fact, that is now coming online. There are companies that are starting to produce those kinds of materials. Chemically, it's identical to meat. It's just produced in a different way that was never near an animal. So you don't have the trophic system of the farming of all the corn, plus all the irrigation that you need for that, plus looking after the animals in the water for that. You just have a much more localized system for growing something that's chemically indistinguishable from meat. So you could have meat grown that way. And I'm really excited to try something. I haven't tried any yet. I really want to get onto that and try it out. Yeah.
I think it's still quite expensive at the moment, but
right. If everybody buys it,
that will come down for sure.
Exactly.
Yeah. Another thing that's interesting is and still talking about livestock, but just very briefly, the way that we've separated our livestock from our crop systems, which means that in really fertile areas people grow just crops, and then in the less fertile areas they keep livestock, but then they have to import the animal feed to feed the livestock, and then the manure kind of goes to waste. Whereas if you bring these two back together and you have crops and livestock in the same location, then again, like we were talking about, these smaller loops in the circular economy, you can recycle the manure, you can feed them the grains you're growing, and actually I think doing that, you can reduce greenhouse gas emissions by 50% or something unbelievable.
Yeah, that's a great example of the whole concept.
You give us a lot to think about. You're not a little suspicious of the lab-grown meat?
Why? I mean, if you can't, if you put it in a spectrum analyzer, you can't tell the difference. Why would we be suspicious? What reason would there be? And something I want to make, actually, I'm glad you brought this up, because it is absolutely fair for people to be concerned about. Yeah, I think, and it's absolutely fair for people to have those kind of concerns, and it's absolutely right to voice them. And it's absolutely right for scientists and, not just scientists, businesses as well, to address those concerns. And I think that's something that you can demand. You can say, look, there are some things that we want. We want to have a sustainable planet. We want to have our luxury, but we don't want to kill everyone to do it. So you guys have got to, give us products that we can do that with. And but we don't want that one because it's scary and dangerous. But can we just talk about it and just figure out a way where it becomes less scary and less dangerous? So, but that's one of the main reasons for putting this book out. Is actually has a lot of, good, solid, basic information about what synthetic biology is all about some of the products that are already coming out on the market from synthetic biology, like synthetic leather, synthetic silk, clothes and textiles. There's and I think it's Adidas, however you pronounce it in the US, that have, they've got a shoe upper made with, synthetic leather that was grown from yeast. And there's other products as well, like packaging materials made from fungi and all this kind of stuff. So, there's no need to be, I can see being scared about putting it in your body, but chemically it's the same as meat. And from a biochemical point of view, it wouldn't be any different. So it's just a question of being sure that you know what's in there. I guess, the cow automatically means that it's natural, and the cow didn't die when it put those things in, so I can eat the cow. So it's just trusting those companies to be transparent about what they're putting into their burgers and demanding that information so that you can be sure and safe and address your concerns. I think that's the way forward. That's where these big deliberations come, where you can have industry people and members of the public having discussions and a politician sitting right there, let's talk about this. Don't just, run away from it.
That's really cool. So we have another question. Very much enjoying the book, but haven't finished it yet. How practical would it be to perhaps work with a small town to implement something approaching a circular economy on a very small scale, as you described in the talk? And I know you just were talking about that a little bit, Claire, but do you have any more specific examples that a small town could do, say, on a city council level?
I mean, I guess trying to find ways to facilitate the exchange of materials between individuals in the local economy. So, I mean, even just simple things at the moment, like free cycle, right? Like you can list your old things and somebody else wants them. Or I've seen ones as well where like apps where you can kind of say, oh, I've got this loaf of bread that's going off. Does anybody want it? And your next door neighbor will be like, oh, I really need a loaf of bread. And so, that kind of, so trying to just prevent things from reaching landfill. I think that's a really good start. But I think, I think there's a lot of really interesting small community initiatives in kind of, sustainability, green energy and stuff like that are popping up. There's a climate charity called Possible who work specifically with individual local communities to try and start implementing more of the circular economy. And I think that is the way we're going to do it. That if you start small and people see that it works, then we can build from there for sure.
And adding to that, the more places that do start, the greater the diversity of approaches. So if every little place starts doing that, then they'll have their own idiosyncrasies that work better for them or work better more globally. And then what you do is then communicate between those communities and exchange ideas with some city, in India or something, where they've got a different way of recycling. And then that way, that's exactly that assay and selection. It's exactly how biology evolved in the first place. So actually getting people to start doing that locally would be a massive thing. Yeah, getting people to think locally about how they could implement it. And there are some bigger scale versions actually. There's in Saudi Arabia, there's a project called NEOM. And Saudi Arabians have been thinking about the fact that oil is probably going to be phased out over the next 20 years. And so they think, okay, we need to get a better livelihood. So they've actually they're actually in the process. It's got a budget of $500 billion. And they are in the process of constructing a completely sustainable city, which is stretched out along a railway track in Saudi Arabia. It's like a really long, like 100 miles long, but 3 miles wide. And they're building like a complete infrastructure, the whole transport system, all the water systems, they use desalination and it's all driven by solar power. And so they can get all this beautiful technology like integrated and build testing technologies, which they can then sell to other countries, say, hey, build a city like this, we know how to do it. And so, that is actually being built as we speak, which is fascinating.
I don't know if this is kind of something that's kind of getting into the headlines in the US or not, but over here at the moment, there's a lot of talk about this idea of the right to repair. So, you know, this idea that you should be allowed, you should legally have the right to be able to open up a device you've bought and fix it and change it, and because it's your device. Whereas at the moment, you know, you void your warranty and you won't be able to get the parts anyway. And I think, you know, this kind of local communities where they're implementing projects to teach people the skills to repair their own devices. I think that's a really interesting area, and I think it's really important.
Yeah, that's a really good point. I'm already thinking about all the different things that I need to fix so that I don't have to throw them out.
Right.
Okay, so we have a couple more questions. What other books would you recommend to a reader looking to learn more about sustainability?
Yeah, I recommend one called A Wealth of Flows by Ken Webster. If you want to get more involved, I mean, that talks about the relationship with capital and how circular economy changes the relationship with capital. So that's really interesting from an economics point of view. There's also, there's another one which I love, which is called Systems View of Life by Fritjof Capra, which that's a more technical science look, which goes and talks about dissipative systems and how biology works as an ecosystem, how it works as a whole complete system. Have you got any more there, Claire?
I'm staring at my bookshelf trying to think what I've read recently.
I've read so many books yet, and it's just like, which one? So System View of Life, those are two really great ones. There's I was trying to think. There's a whole bunch of books referenced in the back of the book which we talk about, and I'm just drawing a blank right now. It's one of those horrible blank memory things, but those two books I can recommend straight off the bat. And yeah, okay. So
two is a great number.
Yeah, that'll do for now. So
thanks for carrying me on that one, Chris.
No worries.
What has surprised you the most in working on the book? Any discoveries you didn't expect?
The 3D.
I was actually.
Go on.
I was going to say I was actually amazed, and I'm a biologist, so I should perhaps not have been amazed, but I was amazed by how far and how many advances we've actually made in synthetic biology. So that there's a lot of commercialized stuff out there now that I just didn't know was there. So I think that was really exciting to find out just how far we'd come since I sort of started learning about this in my biology degree.
And for me, I think there was something we actually put in the book. We were just doing a kind of survey of modern manufacturing techniques, and there's this one thing called explosive manufacturing, which really highlighted the point we were making about enormous energy expenditure over a short period of time. And that's where they literally set off a detonation of explosives with a workpiece held next to a metal former, and you use the force of the explosion to shape the metal. And that's that was a technique they used to make the Saturn V rocket engines. I believe they're actually using a process. I'm not 100% sure about this. I know that SpaceX is using additive manufacturing, but I think they also use explosive forming in some of the rockets. But I have to verify that. But I think it's still being used now, like this idea of explosive forming. I love that idea.
Yeah, I think for me, making that connection between the circular economy and the potential for us to live, or to expand our civilization to other planets, like I kind of, we discussed that connection sort of briefly, but the more we got into the book, the more apparent it became. And now, even now, like writing articles as a journalist, I'm constantly being confronted by this idea that, if we want to go out into space long distance, if we want to create colonies on Mars, we're going to have to figure out the circularity issue. And and we need it here on Earth. So whichever way around, whether we invent it for space and bring it to Earth, or invent it for Earth and take it to space, I think that's really exciting.
Yeah, that's right. I think we have, whichever direction you go, we're confronted with this barrier of circularity. It really is true. So we have to solve this problem. We can't get around it by bringing materials from asteroids back to Earth, because it's not going to work. You just end up
not practical.
The waste here. Yeah, and in fact, another book that's really great is Gödel, Escher, and Bach, and that's more relevant for the computational chapter. When I go into some depth on computation, the Gödel, Escher, Bach book really talks about some of the underpinnings of how computers really work. But yeah.
Awesome. Well, that's about it. We're at 1:30, but before we log off, do you guys know what you're going to do next? Are you going to write another book together? Will there be a sequel?
We haven't talked about it.
Maybe Brave Mars about our colonization.
I mean, there was so much material that we had to cut out. I mean, there's definitely enough material. Maybe it might be nice. One idea I had was to focus on each chapter and then do a sort of explosive thing on each chapter and say, okay, this is that chapter in more detail. But that would be 10 books. That would be a lot of work.
One thing that we're discussing that may or may not turn into something real is possibility of doing a bit of a podcast and talking about some of these concepts with some other people. But yes,
that would be great. Yeah, to get some experts on those topics in and then say, is this a good idea or a bad idea? And use the book as a kind of frame and then to build up a following. I think that would be a really great idea. Well, I'm into that.
All right, I'll listen to your podcast.
Excellent.
In the meantime, everyone can buy the book on our website, mitpress.mit.edu. I shared the link. Let me just share that one more time. I think something about the link cut off, but it is on our website, mitpress.mit.edu. It's still cutting off, but you'll find it, guys. All right. Thank you so much for joining us, Chris and Claire.
Thanks so much for inviting us.
Thank you.